right? So these are the rules, right? And we're going to go over the rules. And somebody asked earlier, should you memorize them? And I would say no, more than that. Every kindergarten student should have them deep in their soul. All right? They really are obvious. All right. So now let me tell you something else. All right, so yeah, you know. All right, so hopefully we didn't close Zoom. I made it this table. All right. I'm not a book reader. I haven't read all the books in logic, right? I just said, how do I want to organize this? And I organized it into 2 columns. You would go away. Things that we're using, right? Right, we're building from the top down and we're building from the bottom up, right? From the top down are the rules that help you use things. And from the bottom up are rules to help you prove things, right? So let me show you what I mean. All right. So here, what we're doing is using an and. All right. Suppose up at the top, things that you have already, you have an and you want to use it. You want to come from the and, you want to use your and, right? So it says, suppose I've already have an and statement and I want to use it. How might I use it? Well, here's a funny and statement, right? It's big and ugly, but we're going to talk a minute later about why it's an and statement, right? And's at sort of the last thing done, right? And so it's an and statement. And what does this and statement say? If you know that alpha and beta are both true, then you know that each of them is true separately, right? So you can use the and to conclude that this first one is true, right? Does that make sense? I just said this is true, and I purposely made it big and ugly, right? To show you that we take big ugly thing and we use this rule. In fact, I'm going to almost go out on a limb and say, whenever you know an and, always apply this rule to separate that you know them separately, right? It just simplifies things. Everybody got that? All right. So here is something that I need. And it has an and. So I say, I'm trying to prove this and. How do I prove ands? Right? What I did is I looked for all rules that have an and on the right-hand side, right? The other has ands on the left-hand side. So what are the rules that have an and on the right-hand side? Well, this is one. And what does it say? If you want to prove an and, one way to do it, in fact, maybe the only way to do it, is you prove each of them separately, right? They both have to be true. So what do? I tell myself that I have to, in fact, hey, you know, I'm going to change the slide, everybody. I'm going to change, let's see here. How I'm going to change it is I'm going to move this up here. I'm going to make this yellow, right? And I'm going to move this line up here. I'm going to make these green, right? And one of my problems is which green is right. So why is this better? And these are new slides. This is the first time anybody's seen them. Why is this better? Is because I'm not claiming I have them yet. I'm claiming I need them, right? Here, I had this, and hence I have this, right? That's moving down. Well, here, I need this, and hence I need these guys up here, right? Does that make sense? That's what I meant to do. Everybody follow what we're doing here? We use the have rules to build your yellow down. We use the prove rules to move your what you need up, right? And then hopefully you can see your haves and your needs, and they're close enough that you can link them. Right? Everybody buy that? Yeah?
That's like doing like so suppose if you want to start by from one and then so suppose you want to start from 1, 2, 3,
Yeah.
4, 5, 6, 7, 8. Will that still work? Will that
Yeah. Yeah. Okay, that was a good question. Right? She says, do you have to do it in Jeff's arbitrary order, or can you do it in your favorite order? What do people think? I won't know what order you did it in, right? Because what you're going to do is you're going to write the halves on the top of the page, and you're going to write the needs coming up from the bottom of the page. And the only way I will know is that, oh, why did they put this funny blank space in the middle, right? If you're doing it in text and you got rid of the white space, then I would have no way of knowing, right? Do you know what I'm saying? All right. So when I had it up there as yellow, that would have been the final link, right? When I could have rules like this to link my yellows to my greens, right? All right. Okay. So we're going to spend one of the things, when I teach something to a younger group, what happens is I realize that I'm assuming you know things that you don't know yet. All right. So if you haven't taken one thing that you cover in 2001 is context-free grammars and parse trees. How many of you taken 2001? How many haven't? Right? So I can't assume you know it. All right? So I do have slides periodically. I realized this at some point. In fact, if you go look at my rate your professor, there's somebody who's so angry. They said, I started the assignment and then Jeff came later and taught us extra stuff that we needed to use. Well, excuse me. What happened is I was talking to students and I realized you didn't know parse trees. So I slipped in and taught you some parse trees. All right? So yeah, sometimes I don't know what you know. So that's where there probably are still things that I assume you know that you don't know. And I'm really welcome to you telling me that. And if you tell me you don't know something, I will not only teach it to you here, but I will slip it into the slides for next time. All right? So here's the statement. And I claim, first you got to remember that this is an and because it's upside down. And I always forget that myself. All right? But why is it an and statement and not an imply statement? Right? And it's because it's what's done last. And here I put brackets in, so it's more obvious what's done last. And I will try to put brackets in to make things happier. At some point, we'll do, it's kind of like, is it bed something? There's something that helps you remember the order of operations, right? Bed math, thank you. I knew there was something out there. It was after I went through school. All right, we'll learn that, but for now, let's put in brackets, right? But what is a parse tree? Intuitively, it pretty makes sense, right? What is this? Well, it's the and of this and this, all right? What is this? Well, it's the implies of this and this. And what is this? Well, it's the and of this and this, right? And you can build it from the top down or from the bottom, top up or bottom down, right? Top, down, bottom up. Good. There's a song, everything that goes up must come down. Something, right? Everybody with me here? So it seems obvious that there's no way you can prove something like this unless you know the parse tree, right? And in fact, here's a little hint. If you see something big and scary like that, use your brain to just say, this is the end of something in something, and I don't care what those somethings are, right? It's not all so scary. You start at the top. What is this? It's the end of two somethings. And you don't worry about those somethings until later, right? Everybody get that? So you're trying to say, what rules do we apply? How do we use this? How do we prove this? Well, this is a something and something rule, right? Everybody get that? And so in fact, when I'm asking you to prove something, I'm thinking, Lord, this is easy. Everybody's going to get perfect, right? And then everybody fails it, right? And why is it so obviously to me and not to you? It could be this very issue, right? I tell you that you have or you need this, and if you have it, there's only like 2 rules in the purple table where you have this and you use it. And there's only 2 rules in the purple table where you need this and you need to prove it. So really, there aren't that many options, right? In fact, what you can do, if you really don't know what you're doing, you start from the top and you brute force it down. What does that mean? You apply every purple rule that lets you move down, right? There's usually only 2 of them. And you use every purple rule to move up. And they're going to match. In general, will they match? Maybe not. Why will they match on my test? Because one thing you know about my test is that when you look at the answer in the end, it will be easy. It's an easy proof. It's not longer than this. And here's another question that I'm going to answer her. Do you need the nice slick proof where you only add things that are needed? No. If you add lots of things that aren't needed, yeah, I'll tell you your proof's not as neat as mine, right? At worst, somebody will take off a mark or 2 because it's not pretty, right? Yeah?
So today you taught us like a couple of different methods to do proofs. Will we be required to know all of them?
No.
Great, because I have like a few that I prefer over others.
Well, hopefully you prefer mine, right?
I'll show you one, so I'll say that.
Yeah, so what I want you to learn is purple table proof where you're coming from both directions, right? And why do I want you to learn those? Is because they require a little bit more intuition. They're not just brute force. And when you're actually doing, I mean, should you know the brute force thing? Yeah, you should know it, because if it's a little example, you can brute force it, right? But I'm going to teach, what I need you to learn is this more intuitive sort of proofs, because that's what you need in the world more. That good. All right. So everybody good with what we've done so far? Excellent. So what we're going to do now is argue that the rules, the things that are in the purple table, we can call them rules, we can call them lemmas. We're just going to talk over each of them in a Hilbert proof sort of way and get the intuition that not only they're true from some sort of table lookup, but they're just obviously true things that your 2-year-old should know, right? And in fact, it would be, here's a fun homework assignment. If you have a 2-year-old, go home and ask them and see what they think. All right? All right. So alpha and beta are going to represent something. I'm doing logic, or I love logic. And here, let me say, P and Q were variables, right? Why, anybody remember why I'm using alpha and beta instead? Not a variable. It can be any bigger sentence. Remember we had that and sentence and there was something big ugly here and something big ugly here. Alpha and beta are big ugly things, right? And your brain needs to just turn them into this is alpha and beta, right? Ignore the big ugly thing at the moment, right? Does that make sense? All right. So this says what I said before. There's very little you can prove until you have axioms. You need to start with assumptions. So let's start with, this is a non-logical axiom because it's not true in every universe. But in the universes we care about, I'm going to say it's an axiom that I'm doing logic and I love it, right? It's an axiom, all right? So you've all maybe haven't studied the purple table in detail, but you're a 2-year-old, right? So what's the 2-year-old rule that if you know alpha and beta, what's the thing that you put next? Exactly, right? We in fact, we did it. That was the example we did, right? So, right? We don't prove these assumptions, right? Our conclusion is only as strong as the assumptions are, right? Everybody see that? We're going to prove things, and we're not proving they're true in every universe. They're only true in the universe in which our axioms are true, right? So here we're going to parallel it with Venn diagrams. The and is this, right? So what do we, in each step of the proof, now you might think this is what we're doing here is easy, right? So you're going to tune out. But I'm always trying to teach you something. I'm teaching you how to do proofs, right? And I'm teaching you what do you do in each line of the proof? You add a line that follows from the previous things, right? Using the purple table. And what follows, right? It kind of implies, right? What from these lines up here, what can I easily deduce, right? What follows from this single line? Now, here's another thing. When we were doing those equivalences, this is equivalent to this, which is equivalent to this. But this is not that. This is a weakening, right? Our next line will follow from, but it's not an if and only if. It's a weakening, right? So, what are you doing there? Would you just go away? I really don't like you. Right? And when you touch it, then you have to click again, right? So here, if alpha and beta is true, then alpha is true, right? So we conclude that if the and is true, then the alpha is true, right? Everybody follow that? Right? So here is an implies. Why? Because if everything above it is true, then this is true, right? There's an implied implies. But we get rid of the implies because it's a Hilbert, that turns it into a Hilbert proof, right? In a Hilbert proof, every line one is an axiom, and line 2 follows from previous lines, right? Right, you guys good? All right, right? And here's the rule. And so let me tell you something else about my purple table. I wrote down what I think every kindergarten kid should know, right? I didn't get them from a textbook. I don't know what the textbook calls them. In fact, when I taught 1019, we got a textbook and they were mostly in there and they had different names. So when you write down what the name is, you don't have to write down my name, right? I called it separating and. Why? Because I have an and I separate them, right? Seemed like a good name, right? But if you want to call it something else, the problem with the something else, quite frankly, is it's probably Latin, like Modus Ponens, right? So that's why my names are better, right? If both are true, then each is individually true, right? And it's good to label the rule used, right? So we would say separating and 1, right? Everybody buying this? And as I said, if you're proving something and your brain hasn't turned on yet, then for every and, apply the separating and rule, right? It's not going to hurt you if you do it and you didn't need it. No, let me just add here. Suppose you're in general doing every rule might be not a good thing. Why? Because there are 2 choices here, and then there are 2 choices here, and your proof grows exponentially, right? Now, in our case, the reason it won't grow exponentially is because they start off small, and we know that the proof is such that they'll link up fast, right? So this exponential brute force applying the purple rule doesn't always work. I mean, doesn't sometimes grows exponentially, but all right. Right. The second is a weakening of the first, right? Every universe in which this is true, right? But is the converse true? Right. Oh, here I'm weakening even further, right? Here's another. How can I weaken this even further? Right? I can change it into an or. Right? And here I'm saying, right? Why is it a weakening? Is because our space gets bigger. Here I'm saying my universe is one of these, right? I got a lot of information. My universe is one of these. And when I go down to the next line, I'm forgetting that it's one of these, and I'm expanding to saying it's one of these, right? It's a weakening because I have less information about the universe, right? And then I can expand further and say it's one of these. The universe is one of these. So here, right, we bring in the or, right? Everybody, and you know, one thing I was just typing up new slides on the weekend was this, George says it's bad to have meaning and intuition, right? And for me, they're double checks. You should use the purple table that this follows from this, follows from this. And you should dive into your meaning and double check and say, hey, every kindergarten student should understand this. Is it true that if the and's true, then the or is also true, right? Does that intuitively meaning make sense? And you'll say, yeah, intuitively it makes sense, right? I'm going on the right path, right? Does that make sense? People are wrestling. Are we almost done? Are we done?
4 minutes.
4 minutes. All right. Everybody good with this? All right. So I call this evaluating or building, because you can think about it as in 2 ways. You can think, I know the value of alpha is true, so I can evaluate the or to be true. That's kind of like evaluating. And building is, I know this little structure is big, is true, so I can build a bigger structure, right? Does that make sense? And I called it evaluating build, right? So this is what I said. From evaluating, if I know this is true, I can evaluate this is true. And from building, from this little thing, I can build this bigger thing, right? And then you label it. And then one last line, can you turn this proof around? Right? It was a proof this way. Can I turn it around? Absolutely not, right? Because it doesn't apply the other direction. All right. Sorry for being late. It is a little early for me. All right, let's look at this proof. How many people love this proof? How many people don't love this proof? All right. So remember the first line there is an axiom. That's something that we assume is true. And then the next lines have to follow from the previous line, right? And so if I tell you that one of two things is true, can I conclude that the first one's true? No, come on. Come on, guys, good morning, right? All I know is one of them's true. I have no idea which one's true. And then from that, knowing that one of them's true, I certainly can't conclude that they're both true, right? So is this a good proof? No, it's not a good proof, right? I try to not just give you, this was a good proof. Remember? Each line follows from the previous. If I tell you two things are true, then one of them's true, so at least one of them's true. And as we're going, it's a weakening, right? And that's okay. And the reason, and from the picture, the reason it's weakening is we get less information. There are more universes that we might be in, right? I think there's a slide about this later, but let me say it now. If we just weaken things, one, why are we doing it? And two, how can you ever prove something in the end that's stronger, right? That seems kind of weird. And the answer is that we have rules that these rules just take the previous line, right, and weaken them, while most of the rules take two things, right, and from the end of the two things, construct something that's weaker than the end of the two things, but stronger than any of them individually, right? And why do we do it? I don't know. It's so that we can take lots of statements and conclude something cool. All right? So you see here, I turned it upside down, and it's no longer true because it's not a weakening. It's a strengthening. Right? So here, you can show that it's that what we want is that in any universe in which the axioms are true, in this case, universe is just an assignment of the variables, right? The next statement is true, right? But up there, I chose a universe, and right, you see over there that little universe inside of beta. In that universe, beta is true and alpha is not, and so the OR is true, but the alpha, the first one's not true, right? And so similarly, right? So those, it doesn't follow. So similarly, here's the case where line 2 is true and line 3 is not true, right? So that says this is, oh yeah, this is just what I said. It's you know, how can we get stronger things? And it's because we take two lines and combine them, right? It's good to know that what I think is. All right, so now, so in order to take two things, we need two things, all right? So we're gonna have two axioms, right? The one axiom is gonna say one of these things, at least one of them's true. And I don't know how there can be a universe in which you don't love logic, but let's conceive that you don't love logic, right? So is there anything you can conclude from these two statements? Yeah, exactly. Exactly. So we're all in 1090, and you might not love it, but here, I mean, here this is says the or is true, right? That's line 1, is one of them is true, but we're not doing the second one, and hence what follows is you must be doing the first one, right? Does that make sense? Everybody good with that? And again, I just made up this name. This is Jeff's name for it. I called it selecting or, right? Because you have an or, but you don't know which, and somehow you eliminate, by eliminating one, it grabs the other, right? Everybody following these? All right. And so here we put that it came from lines 1 and 2, right? All right, so this is my purple table saying if you have an and or you have an or, right? You've proved them already. They're your axioms, so you've proved them. What more can you prove from them, right? And you see, the rules are pretty simple, guys, right? It's not like there's all that many things that you can do with these. And so if you're panicking about how are you going to prove something on a test, well, just know that there aren't a lot of choices, right? Yeah. Yeah, this one here. Yeah. One of the reasons I didn't want to make a global change for this one, which I always forget what it is because this has a different meaning. This is a meta system, right? So this says if you have a line in your proof that's this, then you can have a line of your proof that's this, and you can have a line of your proof that's this. You can add this and this, right? Does that make sense? So you can think, well, what are you saying? If you have the and, then you have the and. So it doesn't sound very exciting, but they have different meanings, right? Does that make sense? Oops. All right. So now, one thing, this is go back to who defined and anyway, right? And I'm telling you, you just need to use the purple table, and you can prove anything that's true in all universes, right? So somebody has to define what and means, right? And what this is saying here is that this rule effectively, well, in some ways, these rules define and as well, right? But certainly together, these ones here very kind of explicitly define and. When it's saying, again, we have the two different and symbols. This says that if you have a line of your proof in which you've proved alpha, and you have a line of your proof in which you prove beta, then you can build from those and conclude a line of your proof where the and is true, right? Pretty straightforward. And again, I told you, I named it eval build. Why? Well, because you can think of this as I tell you alpha is true, I evaluate alpha is true, I evaluate beta is true, and now I evaluate this is true, right? Or you can think about it as building a bigger structure, right? And it just comes from this line here. And then what's this one down here? This one, it tells you, if I tell you that one of them is false, then the and is false, right? And you can see from the table that if alpha is false, then the and is false, right? Everybody buys that, and that's, again, And then, now the funny thing here, if I tell you that alpha is true, right? I don't know whether the and is true, right? Whether the and is true depends on whether beta is true, right? Does it make sense? But the truth of, we can narrow it down, we can simplify it, that the truth of the and now just depends on learning the truth of the beta, right? So we did one of these before. In fact, I kind of slipped that slide in, forgetting that we hadn't done it yet, right? So this is just saying, if alpha is true, then when beta is true, the and is true. When beta is false, the and is false. So in some ways, we can simplify true. Oh, here's a typo. I think we're supposed to be doing ands all the way through here. All right. So here, one thing you should know is I'm always changing the slides. And whenever I change a slide, I upload them. In fact, that's how I get these, is I download them. Same place you download them. So whenever you're going to look at the slides, you might as well download the latest version. And if you see typos like this, let me know, because last class, I remember there were a bunch of typos, and I fixed all that I could remember, but I could have forgotten some. All right? I'm pretty sure this is, so if the and here, then it simplifies the beta, right? That's what we kind of got here. The and, then this simplifies to that, right? Everybody see that? And if you take a formal course, then there's all these rules about how you can substitute things in, right? But we're just going to say it's obvious, right? Whenever you have a long, scary sentence and alpha and beta is in there, you can take the alpha beta out and replace it with beta, all right? So let's not be too pedantic about it all, right? We're going to just say some obvious things you can just do, right? Everybody good with that? All right, so same with or, right? Well, similar with or. If you know one of them is true, then the whole thing is true, right? The or is true. And the only way you can get a false, in fact, this is kind of what it says, is the only way you can get a false is if they're both false, right? This is the rule. If you know alpha is false and beta is false, then you can evaluate the or as being false. And, oh, and I think you know this already, but if you prove not alpha, then that means you know that alpha is false, right? I mean, that's pretty straightforward. All right, then there's the simplify rule, right? And the simplify rule is if it's false, then the truth depends on the truth of the other one, right? And so we can simplify the or to being beta. All right, everybody good? All right. Oh, this is just because, yeah. Uh-huh.
So if you don't know, so if you, so in the simple version, it says you can out just to give value. So if suppose A is false, then so also the and then turn into false. So you have
Yeah, so what's the question?
But don't you need both values?
Yeah. Yeah. So this says, if I tell you that alpha is true, then I don't know the evaluation of the and. But I know that if I found out that beta was true, then it would be true. And if I found out beta was false, then it would be false. So the the answer to the end is the same as the answer to beta, right? I mean, here I'm sort of said this already, but everything gets in the slides a few times. If I'm told that both are true, right, then I can evaluate the and to be true. And if I've proved alpha and beta, then I can have the and as my next line, right? And these kind of go together, right? Now, this is the one you asked about. Well, no, not quite yet. If I say alpha is false, right, I don't know beta, right? But I can still evaluate not alpha, not the not of the and to be true, right? People see this? Right? If alpha is false, then the and is false. So the not of the and is true. And that's why we write this down. We can't, in our proof, directly say something is false. The way we say it's false is we say that its negation is true, right? So here, if you built the negation of the and, then you can build the you build the negation of alpha, you can build the negation of the and, right? And then this is the one you're talking about, right? Here I have this big long thing, right? Remember we were doing Davis-Putnam, right? Where that tree, and I try setting alpha to be true, right? Now in my little part of the tree, I know that alpha is true. So I want to simplify. Can I evaluate the whole thing? No. But can I make it simpler, right? And if it's simple enough, I can prune off this tree, right? So I can simplify it by saying, well, I don't have enough information, but I can simplify it to just being beta. You following this little thing here? Yeah, excellent. Right, this piece is true if and only if this is true, right? Everybody good? Versus if this is a line in my proofs and I'm saying you can substitute it in, right? All right, now we're doing implies. We're we're just going through the purple table, right? If loving it implies that you do it, then what can we conclude from this? Right? You can think, right? What am I get here? What's not true, right? Right? See here, we got a little picture. We're over there, so we can go there. Oh, here I'm adding a new axiom, right? The new axiom is that I love it. Now what can we conclude? Right? If you love it, and loving it implies that you're doing it, we've eliminated a lot of the universes, right? So we conclude that you're doing it, right? Everybody good with that? And if you're good with Latin, and it's called Modus Ponens, right? And why did I call this one Modus Ponens? It's because I happen to remember it, right? It's kind of a classic. Right? What are we doing? All right, so this is just pointing out people do get confused by things, right? If I tell you that loving it means that you're doing it, it doesn't tell me that you're loving it, does it? In fact, it doesn't tell me anything about whether you're loving it or whether you're doing it, right? In fact, all it tells me is that you're not loving it and not doing it, right? That's the only thing it's telling me, right? If I love it, it doesn't say I love it. Right? There are universes, right? Here's a universe in which I don't love it, right? Everybody kind of follow that? Okay, then we say what else follows from this? All right, what about this? Does this follow? Right? Everybody, right? No, A implies B doesn't mean B implies A, right? It's sort of a subset thing. So you should know, no, this hound, you're a hound, you're a dog. If you're a dog, you're not necessarily a hound, right? Right, so here's what I'm doing is here's a universe in which the first is true and the second is not true, right? It's not too hard to find such a universe. In fact, if right, on a test, if I said, prove to me whether or not this is true, and you see it's not true in a particular universe, then proof by example, you can prove it's not true, right? In fact, I saw this little video yesterday that said, you never can prove that, well, it doesn't really matter. You never can prove things are true. You only can falsify them, right? And this is kind of what they mean. It's when there's an for all, you can't prove for all so if there's an infinite, right? All right, so, how about this one? If I love it, then I'm doing it. Does that imply if I'm not doing it, here I'm outside of the beta, what do you conclude that you're loving it, right? People good with this? Right? And that's called the contrapositive. Yes, quick question. Sometimes I bring chalk with me, but there's no chalk. Is there something there? Oh, here, look at this, right? So this says if this is true, then this is true, right? If I'm a hound, then I'm a dog, right? But if I'm a dog, does that imply that I'm a hound? No. If I'm not a dog, does that imply that I'm not a hound? Right? Because why is it? Right? If being a hound implies that I'm a dog, but I'm not a dog, then I can't be a hound. Why? Because if I was a hound, I would be a dog, but I'm not a dog, right? How are people doing with this? Anybody in the back feeling lost, or is this just flowing okay? Good, thank you. I love you people in the back, right? Oh, yeah, there are various statements that I find funny. People say, if you want to know the truth, you'll tell me. And I kind of laugh because I know that means you're going to tell me whether I want to know or not. That was just my little joke. Right? Oh, this is, we're building up to if the statement gamma implies beta, right? It's true. If beta is true, then we're good, right? Doesn't matter about the first, right? Here's another one. You know, if I say there'll be no racism when hell freezes over, right? Well, the implication is that hell's never going to freeze over, right? So there will always be racism, right? I mean, that's the contrapositive. And here's another one. If the alpha is true, right? Oh, sorry. If the alpha here is false, then this statement is true no matter what, right? That's the point of the Yeah. All right. All right. And then this is a joke that it's hell in Texas, but it froze. All right, so here's some of our rules that we wrote already, right? Everybody good with these rules? This one, here's the contrapart, right? If this one says it's not true. Oh, this one says either alpha is false or beta is true, right? And I don't know. Everybody good with those? All right. And this is kind of what we did before about defining the table. We're doing it just the same way as we did before, right? If beta is true, then, right, you got it for sure, right? And if alpha is false, then you've got the implies for sure, right? You see here, if alpha is false, right, it's like, remember, I'm writing code, and if the precondition is true, then the postcondition has to be true. Well, if you give me an input where the precondition is false, then I'm not going to be in trouble no matter what I do, right? This one is just reading off the one false statement, right? If alpha is true and beta is false, then it's not true, right? And then what are the simplifying? We did this before, right? If alpha is true, no, alpha is true. Yeah, if alpha is true, then the truth depends 1-to-1 whether beta is true, right? So alpha being true, you can simplify this to whether beta is true, right? But here's the tricky one. If beta is false, then it flips. If alpha is true, then the sentence is false, right? And if alpha is false, the sentence is true, right? Everybody kind of follow that? You can just say here, if beta is false, then I can simplify this to this, right? Everybody good? All right, and this is the same sort of evaluating building thing, right? Here I have this big, ugly thing to evaluate, and I plug in false there, right? Which makes that true, and then I get, right, the whole thing, right here, this is false, so this is true, and this thing here on the right-hand side is true, so the whole thing is true. Right? People see that? Yeah. And similarly, we can start building, right? From knowing this, you can build bigger things. Right? These are just more examples. Oh yeah, what's interesting about this example is it's a tree, right? I built something, and then I built something separately, and then I put them together, right? So this is an example of taking two. This is where we're simplifying, right? And building. And this is where we're simplifying the other direction, right? This was a complicated one where if alpha implies false, then it boils down to not alpha. All right, everybody good? This is getting a little dry, and I think dry and obvious. Are we doing dry and obvious? Not dry, not obvious? We're good. Everybody good? Everybody love logic and doing it? We got some honesty here. We got some ass kissing back there. It's all good, right? All right, so here's just another one we throw in for fun, right? Remember, this is parity, right? Parity means an odd number of them are true, right? one is true or the other is true, but not both and not neither. So if I plug in that this is true, right, then that counts. We got our true already, right? So the other better be false, right? And equivalence, if you got alpha implies beta, you have beta implies not alpha, then you got an if and only if, right? That's just definition. And then transitivity says if I can get from home to St. George Station, and I can get from St. George Station to York University, then I can get from home to York, right? Called transitivity. Oh, why did I write it down twice? Right? Remember what the using is. We write it down over here if there's an applies on this side, because you can use it. And you write it over here if you can prove it, right? So it needs to be on both sides, right? That way, if you got an applies on either place, you can just go and see hey, I can use this rule, right? All right, modus ponens. All right, we got to fill in this one, right? This says, how do I use the implies? If I got alpha and alpha implies beta, then I get beta. Everybody know that one, right? Now, anybody want to tell me, how do I prove that alpha implies beta? We're going to have provers and, oh, no, this is oracles. I've made up a new role. It's called an oracle, who's going to assure you of things. All right? And I think I've added the oracles. The oracles were later slides, and I think I brought them up. So it's called deduction. All right? And in some ways, we might argue it's not formally part of your proof system, right? Because the proof system, Hilbert proof system, is just these lines of proof, right? And you can do it just lines of proof, but we want to bring in intuition. And so we're going to stretch the definition of a Hilbert proof to have indenting, all right? And so what we're going to do is we're going to assume that alpha is true. Do we know alpha is true? No. We're just going to pretend we're in the universe in which alpha is true, and then we're going to indent, and then using that information, we're going to prove beta. All right? So now I think we're going to later talk about proof by cases, right? But here, suppose alpha is false, right? Then alpha implies beta is automatically false, right? And so proof by cases, we got that one handled already, right? So we're just going to have the convention that we never handle that case because it's just not a case that matters, right? Right? So instead, we're going to temporarily assume that it's true, and with it, we're going to prove beta, right? So here's how we're going to, this is somewhat me and somewhat standard, right? It's nice to tell people where you're going. In fact, news media that you don't pay for does the opposite. They want you to read past all the ads, so they make a point of not telling you what you want to know until the end, right? I like the first sentence to tell me what's going on, right? So here, first sentence, I'm going to prove something by deduction, and my goal is to prove that alpha implies beta, right? So what's the first line after this is always going to be, so the line there is not something I'm going to fill in, the line is telling me I'm indenting, right? I'm indenting, and I say I'm assuming alpha. How am I assuming it? Well, because that's what we're doing, right? And then I go through, and somehow from alpha I prove beta. And then I conclude, right? Say I undent again, right? And I say deduction, conclusion, and I got alpha implies beta, right? People buying this, right? So within the indenting, the reason you're indenting is that when you're reading it and you see an indent, you say, oh, I must be assuming something. And you can go to the top of the indent to see what it is you're assuming. And as long as you're indenting, you're in that world, right? Everybody good? All right. So here, I want to prove if I love it that I'm doing it. So I assume that I love it. And then obviously, anything I love I would do because I'm an active person, right? Hence I'm doing it. And so I conclude that if I love it, I do it. Right? Everybody follow this proof? Oh, and here this is Jeff's story, right? And let me tell you the story, right? So in our story, we're going to have 3 characters. You might as well learn them now. We have the prover that's trying to prove things, the adversary who's trying to prove it's false and giving you a hard time, and the oracle who's up on a mountain and can tell you things, right? She's a burning bush. So here she is, right? And so, right, we're going to talk about her a lot later. And but right now, we're going to sort of do proof by cases. I said it already, right? There are 2 cases. A is either true or false. And if it's false, then while we're down here and it's false, we're going to assume it's false, right? In fact, later in 3101, we're going to talk about dynamic programming. And we're going to do, it's all based on, you come down here and now we're going to assume something, right? And then you come over here and assume something. For some reason in dynamic programming, I call the oracle the little bird. She tells you something, but same idea. This is a big bird, right? Right? Why is it false? Because we're assuming it's false, right? And in this case, we're done, right? So lizards nurse their young implies that lizards are mammals, right? Is that a true statement? How many people think this is a true statement? That if a lizard nursed its young, then it would be a mammal. True. How many people go for true? How many people go for false? How many people have been paying attention in this class? All right, so, you know, this is kind of a funny thing, right? Is this true? Here's, I think, the thing that gets you mixed up. There are 2 things that get you mixed up. First, you believe that you live in your reality on Earth, right? And we don't here, right? In this class, we're not on Earth. So don't assume anything from Earth. And the second you have the sense of, am I asking you, is it a tautology, right? Am I asking you, is it true in every universe? I mean, that's another thing, right? But actually, I take it back. We are in our Earth here. In our Earth, do lizards nurse their young? No, they don't. The precondition is false. So am I going to get in trouble? Is this true? It's always true, right? It's true because the first statement is false, right? And so I put this up to mess with you. You know I did. All right? So this is true. Right? In fact, I mean, look at the contrapositive. The contrapositive says if lizards are not mammals, right, then they don't nurse their young, right? Does that feel more true? Feels more true, right? But it's the contrapositive, right? A implies B, not B implies not A. So this is true, right? In fact, or you could say this is what Darwin says. If anything nurses its young, in fact, you could say the definition almost of mammals is that it nurses its young, right? All right, so this is true no matter what, and we're done. We don't have to worry about this case, right? Now we go over to the other case. And in this case, the oracle's assuring us that it's true. And why do we say it's true? Because it's the case we're dealing with, right? And people are often coming back to me and said, why are we assuming it's true? Well, it's just one of the two cases, and we're dealing with this case now. We're now pretending we're in a universe where it's true, because that's the only case in which this statement is contentious, right? So in this case, alpha is only true if beta is true, right? So we have to work hard to prove beta. All right, everybody good? It's called deduction. If you take a philosophy class, they have deduction, and I've never figured out what deduction was, but maybe we can work it out. All right, so what are we doing here? Right, we did this already. This is just saying, while we're in the indent, right, we have this oracle to help us assure that it's true. And why are we going to need oracles later? It's because the thing that we're assuming is true is very complex, and it helps us to have an oracle, right? Give you a hint. Suppose she's assuring you that there exists an X with a certain property, right? She's assuring you that it exists. So how is she going to help you? Somebody says, hey, I assure you that X with this property exists. What are you going to ask them? No, we got the property. There's some property we know. She assures us an X exists that has that property. So then you can say, give me the X, right? Give me an X that has that property, right? Does that make sense? Why can we say, give it to me, and assured that she can do it? Is because we know it exists. All right. Here we're just talking about the powers of the oracle. And I copied these from much later slides because we're doing it here, right? So if she assures me the and, then, no, here I'm proving, right? If I'm trying to prove the and, how do you prove an and? Is you have to prove both, right? And if she is assuring you of an and, then she can assure you of alpha and she can assure you of beta, right? In fact, this is kind of like, remember we're doing yellow coming down and things coming up, right? These are the things that I prove. So if I want to prove an and, then I have to prove the alpha and the beta, right? And here, if she's assuring me of the and, then I can separate them into and beta, right? Yeah? Give him a gold star, right? So one way of thinking about axioms is we're proving if all of these axioms are true, then this final conclusion is true, right? And that's equivalent to proving if these, then this, right? So there's two ways to do it. You can start by putting your axioms up at the top because they're your axioms and you can prove the conclusion. Or you can have what you're trying to prove be these things, give me these things, in which case you start by assuming them and indenting, and then you prove, right? And so really there's no difference between, right, when you get indented, it's like you have new axioms, right? So the oracle helps you assure you that the axioms are true. She helps you assure that the things we've assumed because of deduction are true, right? It's the same. So that was a good question. Everybody good? All right, so the or is a little trickier, right? If I want to prove the or, then I get to choose whether I prove alpha A or B, right? My choice. I only have to prove one of them, right? Now that's great, right? Man, it's not so great here because who gets to choose? If she's assuring you of the or, who gets to choose which one she assures you of? It's not so good. She's just assuring you. It's like our Father, right? Our Father is assuring you that either he will love you for this or he will love you for this. His contract is to get an or, right? So he gets to choose why it's an or, right? So if she assures you that the or is true, right, then she gets to decide which it is, right? And now I'm in here in this assumption world. Well, it may be the A that's true. It may be the B that's true. I don't know which. So I have to handle both cases, right? In fact, what we would probably do from there is say, oh, one of them is true. Let's do a proof by cases. Case one, A is true. Case two, B is true, right? And that's what we're going to do next, right? Right? Everybody see that? Right? I know one of them's true. Well, I don't know which. If A is true, what are we going to do? Right? Everybody good? We follow you guys starting, with earlier days of logic, you were more enthusiastic. I could do a little dance here. Right? You want to dance? Yeah.